and I am a course advisor for ECT. Thank you all for joining us today for today's webinar, which will be presented by our Industrial Automation Program Leader, Dr. Shaalan. For today's presentation, could you kindly just make sure that all the notifications are muted, just to minimize any sort of disruptions that may pop up while the webinar is going on? And I'd like to also turn your attention to our Q&A function. So that's right next to the chat box. If you've got any questions, you can pose them there and we'll answer them closer to the end of the webinar. And for today's webinar, there will be a certificate of attendance, which will be sent to your email within 4 business days from today. And for the recordings and the slides for this webinar, that will be sent to your email within 2 business days. Now, at the end of the presentation, I will be showing the QR code as well as sharing the link for the copy of the slides and the video recording, as well as the certificate of attendance. So this will ensure that you receive your recording, the slides, as well as the certificate of attendance in your inbox. So if it's not in your inbox of your email, could you kindly just check your spam and junk mail? Just to let you know a little bit about ECT and what sets us apart, basically. So ECT is essentially an engineering specialist, and we've got industry-driven programs with UK accredited education, and this is all made possible by our lecturers and instructors who are specialists in the field of engineering. And also we have a unique delivery model. So for this event, or this presentation rather, if you just follow my instructions, so there are no interruptions or anything, and we can have a smooth presentation. Now, today's topic is the basics of SCADA and programmable logic controller systems. And as I've previously mentioned, this will be presented to you by our program leader, Dr. Shaalan, for industrial automation. Dr. Shaalan, if you don't mind, please take it away.
Thank you, Komo. So hello, everyone. Welcome to this webinar on the basics of SCADA and PLC systems. Thank you for taking the time to attend and to listen to this topic. I hope it will be a little bit beneficial, eye-opening a little bit, give you a little bit of information and background knowledge about automation in general. So my name is Abdu Shaalan. I am the program leader for industrial automation programs at the ECT, undergraduate and postgraduate programs. I take care of the programs in general, make sure that they align with the UK higher education specs, and everything is aligned and everything is up to the standards. We focus on student support and making sure everyone is getting the required knowledge and expertise that they might seek in industry when they go and seek employment. So in today's agenda, we are going to talk about the history of industrial automation, the impact of industrial automation, how an automated system works, and what are the tools that are used to execute and write PLC programs. So to start with, to give you a little bit of background and introduction on industrial automation in general, we have to talk about the history of PLC. And when we say PLC, we talk about something called the programmable logic controllers. These are the brains that power control all the modern industrial machineries. It's not a new technology. It is something that existed since the 60s. basically with the introduction of computers. And when we say it is not new, it's the same thing when we talk about computers. Computers are not new, but they are developing over the time, and they're getting improved, getting better, having added functionalities over the decades to get to where we are at the minute. Same thing about the PLCs. They have been developed in a basic way, and over the decades, they have been developed, improved, made more rugged, made more reliable, have added functionalities on different things, communication capabilities, speed, etc. So it's not new, but it has been under development and continuous development since their introduction. So when we talk about industrial automation and we talk about where it came from, what we can see here, we can see control panel. So any modern machinery or any machinery in general at any industry, whatever the industry is related to the manufacturing industry, or maybe different industries as well, oil and gas, food industry, everything that have some sort of machineries in general. Each machine would have a control panel. And that control panel contains and have all the different components that that provides the correct power requirements and all the electrical related components to power up the machinery that you have. We have different types of machineries. We have machineries that can be simple and they are called unautomated. And these machineries, they would require just simple circuitries in the control panel for the power distribution for the different parts and components of the machinery. And it can be as simple as what you can see at your home for your circuit breakers box that distributes the different powers to the different parts of your home. You have a circuit breaker for the lights, circuit breaker for your fridge, for your oven, for different parts and different things that you have installed at home. And that junction box that you have, and you can see it has all the different circuit breakers that you can switch them and flick them on or off. So it can be as simple as that, or with the development and complexity of machineries, it can be semi-automated, which would have some sort of intelligence and some sort of part automated sections of these machineries. They might have a controller and might not, might be relying on relays and different maybe temperature controllers, different elements that can control and measure certain parameters and temperature parameters and health indexes of the machinery. And you get into the fully automated control panels, and these are the machines that work by themselves without any human interaction. So they're fully automated. They don't have or they do not require any human interaction to perform their tasks from the start to finish. And these are the machines that relies on the PLCs and the controllers in order to execute these tasks and to coordinate between the different processes within that machinery. What we can see here, we can see a schematic of control panel, and that schematic is demonstrating the fact that you have a fully automated system that can have a PLC, and this is how the PLC looks like, a controller, and all the different power distribution elements like the circuit breakers, like the communication module, like the main circuit breakers or contactors, relay, an array of relays that provide the connections between the different components, terminal blocks for the interface between the different machinery devices and elements, and the control panel. But going back to that element of the history of industrial automation and the history of PLCs, what used to happen before we had the computers introduced in the 60s? Before the 60s, we didn't have any intelligence. We didn't have anything that can indicate what are we dealing with, or what, or or any elements that can provide any intelligence in our machineries. And we wanted to have an automation. We wanted to have that ability for the machine to carry out tasks by themselves without any human interaction. And this is where you can start to see here, this was called the relay room. So the relay room was basically a big room that is full of different relays and different electrical circuitries. And the whole idea of this was how can we control and make loops or electrical related loops that can create that automation aspects of our machinery. There was no intelligence, there was no programming, there was nothing of this kind, rather than it was singular elements that are carrying out these different tasks. Straight away, when you look at such a photo, you can start to see the complexities that it has. And when the complexities arise, you start to look into what can happen, or what are we going to do when something goes wrong, or what can we do when we want to upgrade this machinery or that system. It takes a long time, it takes a lot of effort in order to carry all of these out. It's not as simple as a straightforward change in the executing program like how we have now, rather than you have to start to amend the whole structure and the whole flow in order to accommodate changes, or in order to diagnose and find out what is going wrong with the machinery, or why it's not behaving differently from what you require. So that was kind of a bottleneck that existed and was causing lots of issues, lots of downtime. And when we talk about downtime, we talk about a killer for the industry. A machine that is sat idling and not producing, not doing the work, this is a loss, a continuous loss, and it can be measured by the minute. So when you look at the automotive industry, for example, and you look at a car factory that produces a car every 30 seconds, you start to think about, well, every minute I'm behind. This is 2 cars that are not made and they are not produced. So that was one of the biggest issues that existed. The installation, the calibration, the upgrade, the diagnostics, that tasks that takes place whenever something needs to be done on a system or a machine or a production line. So in the 60s, the first PLC was created by a company called Modicon, that it is now Schneider Electric. And that was the first PLC that was introduced to the market. Although it had all the required features, it was still not commercially viable, not commercially successful, due to different reasons related to how it works, due to how the operations are happening, and its compatibility with the market. Later on in '73, the company developed the Modicon 184 model, which describes the first PLC to be introduced commercially to the market. You will find a link here in the slides. When you get the slides, please use it to see and to know more about that history. So when we talk about a PLC, what is a PLC? The PLC is a brain, and that brain is responsible of organizing and controlling the entire manufacturing process, or the specific process that it is interacting with. What you can see here, you can see an example of Allen Bradley Micro 850 PLC. On the 2 sides of the PLC, as you can see here, these are the terminals for that PLC. When we think about a brain, we think about that brain by itself is not doing anything, rather than it must have input elements, so things that gives it information about the surrounding environment, and the ability to control and to do actions on the surrounding environment. Like you as a human, you have your eyes, and your eyes gives you the ability, or works as an input to your brain, that it shows you what is around you, and as an output, as a device that exerts and applies changes to the surrounding environment. You have your hands, you have your legs, so you might reach out to pick up something that your eyes see. And this is the whole concept of inputs and outputs. So for the PLC, what you can see on one side, you have all the different terminals for input devices. So all of these screws are actually individual terminals that you can connect different devices to it. Different devices can be digital, and the whole idea of digital is that it can only work based on the concepts of ones and zeros. So it's either on or off. This can be used as physical devices, including push buttons, for example. So a push button is either pressed, it gives you an on signal, or unpressed, so it gives you an off signal. It can be in sensors, like something like a proximity sensor, something like a curtain or a laser curtain system for health and safety. So all of these devices are called digital devices, meaning that they are only operating or have one of two states. It's either 1 or 0. And the other type of devices are analog devices. So the analog devices are the variable devices. Variable devices meaning that it can have wide range of states, something like a temperature sensor. A temperature sensor can measure the temperature, whether it is from negative 100 to 200 or whatever. Different sensors have different reading or different ranges, but it can read from 1, 2, 3, 4, 5, and in between up to the limit of that sensor. Again, wide range of sensors exists in the industry, and different ones are suitable for different applications, whether it is a temperature, pressure, elevation, vibration, humidity, whatever it is. So different ones can be used as analog devices that gives you indication about the surrounding environment criteria. When we look from the other side, we can see the output terminals. So the output terminals, this is where you connect all the different devices that can exert or apply changes to the surrounding environment. Something like turning on a motor, or turning on a light, or turning off a door. All of these are devices, or called actuators, that apply changes to the surrounding environment. And this is where they get connected. They can be digital as well, or analog. So digital, like turning the motor on or off, turning the light on or off. It can be analog, like detecting or determining the speed of a motor, for example. So you want to run the motor at 100, 200,000 RPM, whatever it is. So this can be done with an analog output. Different circuitries and different devices to be installed down the line, depending on the type of motors, for example, or whatever you are using. But we are just saying or giving a very simplistic idea of how things can be done and how it is applied. What you can see here as well, these are examples of existing devices, and these devices can replace certain functionalities or subsidize certain functionalities of the PLCs. So what you can see here at the top, what you have a digital counter. So a digital counter is a device that counts. This is one of the functionalities of the PLCs. If you didn't want to use PLCs for such an application, you can get something like this, and it can do the job for you. Why counters are important in manufacturing setup? Well, you want to know how many are you making. If you are making the factory of Pepsi, for example, and you want to make 100,000 cans of Pepsi every day. So you don't want to just keep making them, rather than you want to count how many you did, and then after the count finishes, you want to stop the machine. Apply this to anything else that you might come across. The same thing can happen with timers. Timers are very important as well, because think about it. For example, if you have a mixer and you are mixing certain chemicals or certain ingredients together, if you are in the food industry and you are making a dough, whatever it is, or making the ingredients for a specific meal. So you want to add these meals together, and you want, for example, to store the mixer for a certain amount of time and then stop the mixer, and so you can keep going with the following or the down the stream processes. And this is where counters, this is where timers can come across. Different timers exist, so you have up timers, you have down timers. Again, too much details, but we are giving the idea of what are the different functionalities. So one of the things that you should know about is the heavy use of relays in industry. So what is a relay? The relay is an automatic switch. What you have at home, if you want to turn on the light, you have a switch. That switch is something like this. You press the switch or you flick the switch, so it will go like this. So you use your finger in order to flick the switch either on or off. So for the relays, it is not using your own power or your own finger to flick the switch on or off, because when you flick the switch on or off, what you do, you are actually creating a connection between the terminals. So on, you made the connection. Off, you did actually break the connection. So I don't want to do this manually, rather than I want to do it automatically. And this is where the relays comes across. So the relays have another layer on top of them. So one layer is the actual connection that needs to be controlled to be on or off. Instead of using my finger to switch it or to flick it on or off, I'm using another layer on top of it. So let's make it something like this. And this layer is another actuation process that takes the signal from the PLC. On the PLC, from the output side of things, says that, well, turn it on. It will create the connection internally between the terminals. When the PLC signal says that turn it off, it will cut the connection internally. And this is how the communication between different devices happens. And this is when you start to talk about how a PLC controls different devices. Why are we using relays? Because PLCs are devices that works typically based on 24 voltage DC. So when you have a device that only works based on 24 volt DC and you want to control 220 volt AC connection between for a motor, for example, or 380 three-phase AC motor, how are you going to do this with only 24 voltage DC signal? And this is where the relays comes across. The top layer, that automatic layer, they are working based on the 24 voltage DC. And internally, once they get that 24 volt DC from the PLC, they start the switching mechanisms for the 220 volt AC, for example. If you have 380 volt, for example, and this is a three-phase, so you have different types, let's say, of relays. So it's not the same as a typical basic relay, rather than you would need certain contactors that can do the same job, but it is still the same concept of operation and how it is done. So when you think about, well, where can I use that automation and where it is getting used and what applications this PLC can give me or functionalities it can give me. So in addition to the counters that we just mentioned and the timers that are very essentials to the process, because at the end of the day, the PLC is like the traffic man. And that traffic man, it's all about organization of the different processes. The traffic man organizes the flow. Let's say if you have a four-way road, so the traffic man will open one way for a certain time and then closes that road or that way and then open another way, maybe for longer, maybe for shorter, depending on how heavy the traffic is at each of the ways. But it is all the sequencing about that organization of the processes. And this is where the PLC comes across. So typically you have the counters and the timers, excuse the bad bitings that I have, but in addition, it has many different elements that it can do. So it has a range of arithmetic operations. It has the basics, so addition, subtraction, multiplication, division, etc. if you want to have the range, if you want to have an average, etc. All of these are arithmetic capabilities PLCs can have. You have the comparison application. So you want to compare if certain values are equal, greater than, less than, and based on this, you start to take decisions. So let's say when the temperature reaches 100 degrees, I want to turn on the fan to cool down the motor. So this is a comparison application that you are using. You have word manipulation like copy, move, etc. And this is about moving different data between different places in the registers internally in the PLC memory. It has the communication capabilities, and this is the modern applications or the modern capabilities of PLCs, that it can communicate, can talk to different devices, and these are the essentials of SCADA systems. So come to this. So communication capabilities to exchange information between different controllers, between a SCADA system, between centralized management systems, etc. Look into anything that you might have within the manufacturing process, any types of machineries, anything that might require automation or transformation of materials from one state to another, or packaging processes, or whatever it is. So think about usually any transformation application. And this transformation application happens using machinery from whatever the type of that machinery can be. And based on this, you can start to see this is where a PLC can come in and can operate. We are not including CNC machineries, for example, because of how the tasks that they carry out are more complex. And whenever you want to think about PLC, think about sequencing of operations. You want to do one thing after another. It's not about being specialist in one specific element, that you're computing specific, doing certain computing elements, etc. Rather than you have certain tasks and certain stages, and you want to have a sequence of operation between all of these stages. This is where the PLC comes across. So, as I said, CNC machineries work based on computers and different way of programming and different ways of how it works, like G code and M code, etc. So we're not going to get into this. It's not part of it. Rather than it is, we are more focused on the sequencing of different processes. As I said before, we have two different types of inputs and outputs. So the digital type and the analog type. As we said, the digital ones have only the representation or the capabilities of being running used on one of two states, either off, a 0, or on, a 1. And this is how they are, and this is how their operation works. And the analog type is when you have variable elements, like how we can see here, and you have the capabilities. This is the register size and how many steps it can accommodate. So think about, for example, if you are having a temperature sensor that measures from a 0 to 100 degrees. So you can have 4,000, and this is 12 bits register. So it has the sizes to accommodate 4,095 steps in between, meaning that you can have 1.01, 1.02, 1.03, etc. until 0.1, and then 0.11, etc. So you have more steps. The less that number is, the less the steps that you can have in between, and the less the accuracy. So this is a typical register size in general within the PLCs, and it satisfies majority of the application that it is interacting with. So how does PLC works, and how does it get programmed, and how can we use it? So when you talk about a PLC, or when you think about a PLC, you think about, well, it's a device that it is designated for engineering applications. In the past, how it has always been, let's say before the 2000s, in general, engineering had either electrical or mechanical specialists. So it is either a person that knows about electrical elements or a person that knows about mechanical elements. When you think about that, you think about when you start to realize that engineers don't like programming. It's not their area. It's not something that they used to do. It is something new to them that is now emerging and became fundamental requirements for every degree, almost, that you at least need to know how programming works. But generally, engineers don't like programming. If you think about the programming language, whether it is a C, whether it is Python, whatever it is a Java, whatever any of these programming languages, start to think that, well, engineers hate it. They don't like it, they don't understand it, they don't want to interact with it. It's either I'm a mechanical person, I want to go around and fix mechanical stuff, or electrical, that I like electricity, I like the connectivity, etc. So this is my area in general. So this is when PLC developers or the companies came up with programming languages for the PLC. So they came across and they came around and they thought about it and they said, right, let's make something graphical. A method that is easy, simple, straightforward, that engineers would be able to like it, to understand it, and to interact with it. And this is where the PLC programming languages family came across. So in general, for PLC programming, we have two families. It's either the graphical languages or the textual languages. Graphical languages, they are purely drag and drop and minimal programming, down to no programming really. And it is all about the connections and creating the connections in a way that is simple and straightforward. For the textual side of things, you have languages that mimic the higher level programming languages like the C, the Python, etc. Mainly the C, but again, a little bit different. They are not exactly the same, but they were designed and developed for the people that might have interest in the actual programming languages, and they are not, and they are happy to do it. So for the graphical languages, we have three different types. We have ladder logic, we have functional block diagram, and we have sequential functional chart. Ladder logic is the most simple language, straightforward, simple, and easy. But when you have a big project, big system, it can get messy. For the function block, it condenses things a little bit into different blocks of functions. For the sequential function charts, again, more dense, more about sequencing. Think about, for example, if you have a traffic light and you want to write the program for it, sequential functional chart is the go-to for such an application. For the textual languages, you have instruction lists and you have structured texts. So in general, you mainly have all of these 5 languages, and these 5 languages follow IEC standards 61131. Everything in life has a standard. If you want to build a house, the foundation have a standard. If you want to paint your wall, the paint that you're going to buy has a standards. And these standards make sure that this is safe, this is recognized, this is how it should be done, this is how the process can be safe and can adhere to different required elements, whether it is health and safety, environmental, operations, usability, etc. So when you look into the PLC languages, this is the go-to standard that is recognized worldwide for programming language for PLC, IEC 61131. So what we said so far, we've been talking about, well, the PLC is the brain, and you might have some inputs and you have some outputs. So looking at the output side of things, what can the PLC control? We give basic example that it can control a motor, and it can control a light, stuff like that. And this is very common, and this is main functionalities in general. Any machineries typically would have a motor of some sort to run a conveyor belt, to run the main processing unit of whatever it is, a pump, etc. But on the other side, what we can have different actuators. And these different actuators have different families. You have the electromechanical actuators. This is the motors that you might have. And you have pneumatic actuators, and these are related to the use of air supply in order to apply certain tasks or to do certain tasks. You have hydraulics, very similar to how the pneumatic works. Kind of the main difference in the setup is that you have a tank to store the oil that you are using within the system, and the system is a closed loop system, really. You have thermal actuators, you have different ones. We're not going to get into this, but this is kind of the main ones that exists in industry: electromechanical, pneumatic, and hydraulic. So how can we control a pneumatic cylinder? So what we can see here, we can see a pneumatic cylinder. And what that cylinder does is that, well, in a very basic way, we have a cylinder and it either extends the shaft or retracts. The shaft is inside. So how does it work? Inside the pneumatic cylinder, what you have a plate here, and you have a port here, and well, you have different types. So you have a single acting cylinder, you have a double acting cylinder. Let's look at that double acting type of cylinders. So you have a cylinder, you have a plate here that is a sealing plate, and you have two ports, like how we can see here, port on the right, a port on the left. If you did apply air here, the cylinder or that air is going to push or apply force on that plate in here, so it is going to extend the cylinder. And if you applied air from this direction, from this port, you are going to apply the air on the plate from this side, so you are going to retract the piston of that cylinder until it reaches the end. So these are the two modes of operation for a double acting cylinders. There are different types of cylinders. So there is a single acting cylinder, and the single acting cylinder is a cylinder that has one port. You have the plate, and you have a spring inside. What happens is when you apply air from that side, it will apply the force on the plate, so the cylinder will extend. Once the air supply is blocked, that spring is going to start to pull that the piston back to its original position. So it can apply force only in one direction and then retracts again. It has its applications, it has its usability and use cases, but this is generally how it works. So how can we control this? How does it work? How can we control the airflow between the extension port and the retraction port? And this happens by using something called the directional control valve, or DCV. So the DCV is a device, and that device has many different types as well, and it can work directly with the PLC signals. So it can get a signal from the PLC that says that, well, I need you to extend or to open the port for the extension. So it gets the signal, it is linked to the air supply. So it gets the signal for the extension, it starts to push or to open the port for the extension, to open the air supply to the extension port, and to connect the other side to the exhaust port. So just let that air flow out. And by doing this, that cylinder is going to start extending. Once it does this, you can keep it extended for a certain amount of time. It can be just until it reaches the end. And typically what you can get as well with these cylinders, you just clear this whole thing. Typically what you get with such cylinders, that you can get cylinders that have two sensors. And these two sensors are proxy sensors. And what they do, they detect the plate that the internal plate. So if the plate is in here, so we know that it is retracted. If the plate is in here, so this means it is fully extended. So you can start to create different sequences of operations. So once it is extended fully, now I know that it did apply a stroke. So reflect or reverse the whole operation. It is fully extended, and now I am sure because it did detect the plate at the extension sensor. So the PLC will send another signal to the DCB and tell it, right, now it is the time to reverse the operation. And what I want you to do, I want you to block the air supply from here and connect that port to the exhaust, and then connect that port to the air supply so it can start the retraction process. And once it retracts, the plate is going to be detected here once it reaches the fully retraction position. And again, once this happens, it starts to look into doing whatever next needs to be done. Maybe just create continuous frequent strokes. And this is how it works. It can be done manually. So instead of having a PLC, this can be done with a push button, or it can be done with a relay, simple relay circuitry. Again, different types of it can be used and can be done. So this is how, in a very basic way, how a pneumatic system can operate. When we start to look into from a little bit of adding a touch of automation to the system, what you can have the connectivity with the power supplies. So a connectivity with power supplies is then when you start to have the electric circuit that is related to that pneumatic cylinder connected to it. And by doing this, you start to have that ability or a little bit of a more automation to the system. If the whole system is connected to the electronic circuitries and you're having the solenoids, and the solenoids is basically basic terminologies as well. When you talk about a solenoid, you talk about a baby cylinder, that it is working by electromagnetic field. So it's a small cylinder that has windings inside, and it has a piston. Once you energize this winding, it will push that piston out. Once it loses it, it can retract back or it will be pulled back. Adding a little bit more of automation, you might have, or you might want to have signals or signaling abilities. So you might have an LED or a lamp or an indicator that can indicate or show that, well, the cylinder is extended. If it did extend, so cylinder A is plus, this is usually A plus means that it is extended. I'm going to light up the red indicator. When the cylinder is retracted, I will light up the green indicator. Again, it is good for for usability and for the user to be aware of where the directions of what the state of that cylinder is. More automation, well, you can add a siren. You can add an emergency stop button. If it is extended, I will just make a sound. If it is retracted, I will make another different types of sounds and turn on a different light. I have an emergency stop button now that if anything went wrong in between, I can just press it and kill the whole system or stop the whole system, bring it to a halt. And this is how you can start to build on top of the system and see how can things develop and get more complex. How the automation circuits work, like how we seen in the first slide, when we seen here, go back to it. What we seen here, we seen the control panel. And that control panel, one of the things that we highlighted was the existence of terminal blocks. So what these terminal blocks do, these are the middle ground or the middle connection between the different components within the control panels and the PLC and the outside components or the actual physical devices that you want to connect. If you have a sensor, let's say, for example, proximity sensor that you want to connect to the system, you're not going to wire it straight away to the PLC terminal. Rather than it will have to go through a terminal block, and then from that terminal block, it will go through the whole process, and then it will be connected to the PLC. It might go through another level of connection, so it might go through the relays. Something like this, for example, might be going to whatever devices related to its application and how it needs to be connected. And this is how things can be done. So one more thing that you have to look at is, or spoke about it, is the programming of the PLC. We said that the most simplistic way, or the most simple approach for the programming of the PLC is using ladder logic diagram. Ladder logic diagram works on the basis of having two lines, and this mimics electric circuits, really. So in order to light up a bulb, for example, so something like this, if you want to light a bulb, you want to connect it between the positive and the negative. So like this, and something like this. If you have connection, or a complete connection without any cuts in between, so you are going to have lights. If that connection is broken between the positive and negative, then the light is off. The same principle is used for using ladder logic. What you have two lines. And between these two lines, we use something called the rung. So the rung is programming line. On that programming line, you start to place your inputs. So if you have a push button, if you have a sensor, if you have any signal coming from timers, counters, whatever it is, we're not going to get into that as well, but any sort of input. So inputs usually gets placed at the far left of the line, and then you have the output. And that output can be the light, can be the motor, can be the direction that you want to have for the cylinder, or the signal that goes into the DCV, the directional control valves. So when that input is on, so which means that if it is a button, that button is pressed, for example. So you are completing and making a connection through that line for the power to go to the output. So this means the motor is going to be on, for example. If that input in here is not connected and it is broken, so the link is broken, so meaning that you don't have a connection between these two lines, so it means that this output or that motor is not going to get power, so it will turn off that output. And that's the same principle. This is how it works. What you can see here, this is a very basic example of a ladder logic. So you have an input, and that input signal is to extend the cylinder. As an output, that output is going to be the signal that goes to that directional control valve, to the extension, or to allow for the extension to happen. Another line or another rung is the retraction. So retraction signal. So once that retraction signal is on, so the connection is on, so that output for the retraction is on, so it is going to retract the cylinder by energizing the retraction position. And you start to build on top of this for the sequence of operations and how things can interact together, etc. And this is a sample of how kind of a full control program for a simple pneumatic cylinder can be established and operated. So what we've seen, or what we spoke about so far, we spoke about a level of automation that happens or is placed at this level. When we talk about industrial automation, we talk about 5 different levels. We have level 0, and this is the field devices. These can be all the inputs and all the outputs, all the sensors, all the motors, all the cylinders. These are the devices that applies the job or do the job. And then you have level 1, and this is the control level. The control level is the PLC that is connected to all of these field level devices and can control their operation. Then at this level, you have established one machinery. What if you have 10 machineries, 100 machines on the factory shop floor, and you want to connect them all together for the sake of monitoring and observation and the change of parameters. Instead of going to each machine every day or every time of the day or the shift, or whenever you have a work order that you want to change certain parameters, or you want to monitor certain criteria to make sure that the machines are working how they should, they're not stopped, they're not broken, they are operating how they should. You want to keep an eye on how many already has been done, etc. All of these different things, instead of going around as a person on any machine, for every machine, if you say, let's say, for example, you have 100 of these machines. Now it looks like a TV, but anyways, so instead of going around for each of these machineries, in order to find out what is happening or to change parameters or to restore operations, etc., you have the SCADA level or the supervisory level or the optimization level, different names. So a SCADA level, this is typically a big room with many screens, like how you usually would see. And these screens have the monitoring capabilities and have all the different visuals that can indicate different machineries, how, if the machines are working, if they are not, if everything is how it is, if there are any changes that are required, etc. And can optimize it, can look into it, can do all of that, all of these different things. Up to here, we are talking about operations. We're talking about doing the tasks. You start to go to level 3 and 4. This is when you start to get into a little bit of management. A little bit of management, you want to plan for the whole day operation and schedule what needs to be happening today, what needs to be happening in that shift, etc. You start to go a little bit over to the MIS level. So, or corporate management level, this is when you start to have multiple things interacting with that. And you start to have supply chain, you start to have orders, you start to have employees details, you start to have everything that is related to the factory, as well as the control and the production. So this is when you have that big system that controls everything within the company, like an Oracle system, that this is the backbone for mainly almost every company worldwide. But something like this. So a big umbrella, that controls everything and has everything underneath it that can give that whole idea and the whole operations and the capabilities that they're looking for. So this is it for today. Time flies by. And as we see, I hope that made sense to you, give you a little bit of idea into how automation works, what is automation in general, and give you a little bit of understanding of how different systems operate and how machineries at modern factories work. I don't know if you are an industrial engineer or if you are working in the sector or you're still seeking education, but industrial automation in general is one of the areas that is essential, that is always required, that is always having a shortage, because there is no enough people that can operate these machineries, build these machineries, maintain these machineries, and make sure that they are working how they should. So thank you for attending today. Thank you for listening to this topic. I hope that was beneficial to you and worth your time. Thank you. I will hand it back to you, Coleman.
Thank you so much, Dr. Shaalan. As always, it was interesting and informative. And once again, thank you to all our attendees for joining us today. So if you guys do have questions, please put them in our chat box, or alternatively, you can put them in the Q&A box. So just to let you know about our courses coming up. So for our bachelor's programs, we've got an intake for September. The next one will be next year in January. And then for our master's programs, we've got an intake for October, and then the next intake will be in February next year. So we also do have, as I've mentioned, a certificate of attendance for this particular webinar. And you can either capture the QR code there, or you can just use the link that I've put in the box, and you can just fill out the form, and you only have 48 hours to fill out the form. So from now, you've got 48 hours to fill up the form. If not, unfortunately, you'll not get the certificate of attendance. Please ensure that your information is correct so we can direct the copy of the slides, the recordings, as well as the certificate of attendance to your email. So for our Q&A session, we've got 5 minutes for that. So I do see that we've got a question. And the question.
Yeah.
Oh, go
So
ahead, Dr. Shaalan.
that's all right. So to answer your question, SCADA it's a supervisory level. So it's not about the control itself, rather than it is supervising what is happening and keeping an eye on everything. You might be able to change certain parameters, operation parameters, but they are not there. The SCADA is not there to control or to mainly control the breakers. It is all about controlling or keeping an eye on the controllers that control the breakers. I hope that makes sense. So you cannot really skip that level of controllers. This is the workhorse, and you have to have it. And then if you, on top of it, you start to have your SCADA system. Yeah.
Thank you so much for that. And just for our attendees, I have included the link for the certificate of attendance. And then I've also included some information with regards to our 3-month short courses. And those are professional certificates of competency. And we currently do have a discount from £933 down to just £599 for the course, for the entire course. And I've also included our link for the website and the events. So this is for the upcoming webinars. Please feel free to use those links, and I hope to see you all in the next webinar. So if there are no other questions, I guess we can call it a day. But once again, thank you all for joining us today. You could have been anywhere else, but you decided to join us. So we do appreciate your attendance, and have a lovely day further. Thank you so much.
Thank you, everyone. See you later. Bye.
Bye.